Now, let us see if there's a relationship between determinants and elementary operations. Now, which of the following do you think is easier to evaluate or find the determinant? A or B? If your answer is B, then that is correct because we know that this is an example of a upper triangular matrix, and to find the determinant of this matrix, we can just multiply the entries in the main diagonal. Whereas in A, we can do it via cofactor expansion, which is kinda difficult or at least longer than finding the determinant of B because we don't have zeros to cancel out. Now, if we can rewrite A in such a way that it can turn into an upper triangular, then it might be easier for us to evaluate the determinant. And if you would remember, to rewrite an equivalent matrix with zeros at the end, we use our elementary row operations. The question is, would the elementary row operations affect our determinants? Let's figure that out. So first, let's try to find the determinants of these three matrices here. So, in number 1, the determinant of that matrix, this one here, would actually be, that's 2 times 4, minus negative 3 times 1, that would actually be 8 minus negative 3, that would be 11. And then, here, the determinant of this matrix would be 1 times negative 4 minus negative 3 times 2. That would be negative 4 minus negative 6, which would be positive 2. So there you go. And for the other one here, we have this determinant here would be 2 times 9 minus negative 8 times negative 2, and that would be 18 minus 16, which is 2 as well. Now, let's take note of what happened when we perform an elementary row operation to the determinant of these matrices. Pause the video and try to see if you'll be able to perform the row operation, then find the determinant of that resulting matrix. Alright, so here we are asked to interchange rows 1 and 2. That would mean when we interchange row 1 and row 2 for number 1, our new matrix would be 1, 4, 2, negative 3. And the determinant of this, there you go, would now be equal to 1 times negative 3 minus 2 times 4. And this will become negative 3, well this is 8, and negative 3 minus 8 is negative 11. Take note. For the second one, for row 2 to change, we'll have negative 2 times R1 plus R2. In doing so, I'll just copy first the first row, and in row 2, negative 2 times 1 is negative 2 plus 2 is 0. In row 2, negative 2 times negative 3 is positive 6, and positive 6 plus negative 4 is 2. So finding this determinant here, as we can see, this is actually already an upper triangular matrix, so all I need to do is multiply this one here, which is actually, let's just write it properly, the determinant of this will simply be 1 times 2, which is 2. Take note of that. Finally, for the third one, let's pan that down. For number 3, row 1 is to be multiplied to 1/2. So the resulting, for the second row, I'll just copy that. For the first row, 1/2 times 2 is 1. 1/2 times negative 8 is negative 4. So, having that one, we're now going to have this determinant. I better write it here. 1, negative 4, negative 2, 9 would be equal to 1 times 9 minus negative 4 times negative 2. This is 9 minus 8, which is equal to 1. Take note of that. As you can see, comparing the determinants from the original matrix to the new matrix after performing a certain row operation, it had some effects. When you interchange the rows, it became negative. When you add a multiple of a row to the other row, no change. Here, when you multiplied a row to a constant or to a scalar, 1/2 times 2 rather is 1. So these are the effects of the row operations to our determinant. And this is a theorem. Let A and B be square matrices. So this is only applicable to square matrices. When B is obtained from A by interchanging two rows, like what we saw a while ago here, we interchanged two rows here. This is telling us that the determinant of B is equal to the negative determinant of A. However, when you add a multiple of a row to another row, such as this one here, this is a multiple of row 1 added to row 2 to get to row 2, the determinant actually stays the same between the original matrix and the resulting matrix. And when B is multiplied from A by multiplying a row to a non-zero constant or to a scalar, just like what we did here, we multiplied 1/2 to row 1, the determinant of the resulting matrix should be the determinant of the original matrix multiplied to the constant that you used to multiply in the row itself. So, these are the things that we have to be mindful if we would like to transform a matrix using elementary row operations so that it will be easier for us to compute its determinant. So, to see some examples, let's go to the next video.